As you can remember, on our last lesson, we have started to learn electric field in dielectrics. Electric field in dielectrics, and we have learned a Gauss flux theorem for polarization density. Polarization density, and we have written this theorem. We have written this theorem by formula. Surface integral from P ds, and this is equal to bound charge with minus. Bound charge with minus. And before a lesson before this, before our last lesson, we have learned Gauss law or Gauss flux theorem for electrostatic field. And it can be written like this. According to this theorem, it is equal to US divided by epsilon 0. Epsilon 0 is electric constant. But we have learned the case when we have only free charges. If we have both free and bound charges, we have to take them into account. So it is necessary to change the right side, the right part of this formula. It is necessary to change this to take into account bound charges. So here will be free charges plus bound charges divided by electric constant. Lower index S means that Q is charge inside closed surface S. So QS is charge inside the closed surface S. And let's multiply right and left parts of this formula by electric constant. We will obtain surface integral epsilon 0 E multiplied by ds and this is equal to free charges inside the surface S and bound charge inside the closed surface S. So next step we can make substitution according to the Gauss flux theorem for polarization density. or polarization density. So according to this, it can be written. It can be written as QS minus surface integral of P ds. Surface integral of P ds. And let's add this this to right and left parts of the of this relation. So we will get that surface integral epsilon 0 electric field intensity plus polarization density P ds, and this is equal to free charge inside closed surface S. And what have we obtained? We have obtained this, and this relation is known as electric displacement vector or electric induction vector. So I'll type this electric displacement vector or electric induction vector. Electric induction vector or electric induction vector. This is the same, electric displacement or electric induction vector, and it may be signed by letter D. And it is equal to epsilon 0 E plus P. Epsilon 0 is electric constant. E vector is electric field intensity, and P is polarization density. Let's frame it with red, because this is important definition. And according to this definition, we can obtain Gauss flux theorem, Gauss law. Gauss law is more common name than Gauss flux theorem. Gauss law for electric displacement vector. And this is integral form. integral form. This is integral form, and according to this, we have a surface integral from d ds is equal to qs, and this can be written as triple integral here this is volume limited by closed surface. Vs is volume limited by closed surface S. Triple integral of rho dV. Rho is charge density. Rho is charge density. This is integral form of Gauss law for electric displacement vector. And there is also differential form. Differential form, we know about this. Differential form. Differential form is Gauss law for electric displacement vector. The displacement vector, and this is differential form. According to this, divergence of displacement vector is equal to density of free charges. And this is also necessary to frame in red. Okay, so do you have any questions about this? Do you have any questions? No questions. Okay, let's remember from our previous lesson the dependence of vector of polarization density and electric field intensity. The connection is P is equal to kappa, where kappa is electric susceptibility. In case of isotropic media, kappa is number. Kappa is a number, simple number. So, and non-isotropic media we will not learn. We have no enough time, and non-isotropic media is not necessary. For us. Kappa epsilon 0 kappa epsilon 0 E. Kappa epsilon 0 E. And here we know that D electric displacement vector is equal to epsilon 0 E electric field intensity plus polarization density and let's make substitution and we have obtained that this is equal to electric constant multiplied by open parenthesis or bracket open bracket 1 plus kappa 1 plus kappa. Kappa is electric susceptibility. And it is equal to epsilon 0 E. Epsilon 0 E. Epsilon 0 E. And what is this? Epsilon is relative permittivity. Relative permittivity. Relative permittivity. Relative permittivity, and this is equal to epsilon is equal to 1 plus electric susceptibility plus electric or dielectric susceptibility. This is the property of dielectric. And for isotropic dielectrics that we are learning, for isotropic dielectric, relative permittivity is a number. Is a simple number. And we have obtained that electric displacement vector or electric induction vector is equal to epsilon 0 1 plus the electric susceptibility multiplied by electric field intensity and this is equal to relative permittivity electric constant multiplied by electric field intensity It is necessary to know that sometimes in the internet, for example, you may see this formula is written like this. Only E multiplied by electric field intensity. In this case, you should understand that. Here epsilon means the same as epsilon multiplied by epsilon 0. So this is the same, but epsilon is permittivity here. Here is permittivity. Let's make some different signations. For example, so sometimes you can see this formula in the internet where epsilon with this sign above it is permittivity, and this is equal to epsilon 0. I hope you will not be confused if you if you see something like this. And why is electric displacement vector is useful? It is useful because in the most cases we don't know anything about bound charges. In the most cases we know the distribution of free charges, but we don't know anything about bound charges. And in this case, electric displacement vector is very useful because here we don't need to know bound charges. We need only information about free charges to calculate electric displacement vector. And when after calculating displacement vector, we can find the electric field intensity by this formula, electric field intensity, and we can find then polarization density and bound charges if we want to find them. Okay, and one more thing that is necessary to understand, that maybe one more thing that is necessary to understand, that if we have vacuum, in vacuum there is no any bound charges in vacuum, and because of this, in vacuum polarization density is equal to 0 always, because there is no bound charges. So P is equal to 0. Now P is polarization density, and if P is equal to 0, we will have that the electric susceptibility is equal to 0 too. Is also equal to 0. And it means that relative permittivity is equal to 1. In vacuum, relative permittivity is equal to 1. is equal to 1. Is equal to 1. Okay, do you have any questions about this? Do you have any questions about this theory and this material? No questions. No questions. Okay. If there are no questions, let's continue. Let's continue. The next part is to learn boundary conditions. Boundary conditions on bound of on the surface or on a boundary between two dielectrics or dielectric vacuum. Dielectric vacuum. I have to clean some space or some place on my screen in order to write more formula. In order to write more formula, I'll clean some place. I'll clean some place on my screen. Yes, now I have place. And let's have a look at infinitely small of surface on the border between two dielectrics. Surface between two dielectrics, between two types of dielectrics, or surface of dielectric in vacuum. It can be written like this. Yes, a surface that divides two types of dielectrics with relative permittivities epsilon 1 and epsilon 2, two types of dielectrics. Maybe here we have here we have vectors, electric displacement d1, electric field intensity epsilon 1, electric field intensity in second dielectric E2, and electric induction or electric displacement vector D2. And what is the connection? What is the connection? Connection between these vectors in first and second dielectrics near the border between them. Let's consider an infinitely small closed surface that has cylindrical form. Let's have a look at a closed surface closed surface that is a surface of cylinder. Surface of cylinder. I can draw this. I can draw this like I can draw this here. I can draw this here. This is infinitely small cylinder. And this is its view from a side. From a side. So it can be shown like this. This is ds. The area of upper base of this cylinder minus ds and a vector of normality or normal vector n1 and maybe not n1, let's make it n minus n. Unit vector of normality n. The modulus of vector n is equal to 1, and the direction is perpendicular to the border between two dielectrics. And let's use Gauss law for electric displacement vector. According to this law, we have d ds. There is no integral. There is no surface integral because the cylinder is infinitely small. Because of this, we have no integral here. And according to this, we have d1 ds minus d2 ds. Minus appeared because here we have minus ds. The directions of upper and lower bases of the cylinder are different. Directions are different. Because of this, we have minus. Here. And it can be written. As d1 n ds. d1n is the projection of vector d1 on normal direction, on direction that is normal to the border between dielectrics, minus d2n ds. And this is equal to 0. Why? It is equal to 0 because there is no any free charges. If they are, they have to be taken into account. Separately. But now we are learning case when there is no any free charges. on the border between dielectrics, and in this case QS is equal to 0, so we have 0 in the right part of Gauss law. And from this expression or relation, we have first boundary condition d1n is equal to, so normal parts of electric displacement vector are equal. Okay, what about vector? What about the vector of electric field intensity? What about vector of electric field intensity? This vector is connected to electric displacement vector by this expression, by this formula. So we can read, we can write that d is equal to epsilon 0 e, and as I have said before, that for isotropic dielectric, epsilon relative permittivity is a simple number, and if this is a simple number, we can write this formula without vectors. Epsilon 0 e. Epsilon 0 e. And because of this, we have that modulus of electric field intensity vector is equal to d divided by epsilon 0. Epsilon 0 for isotropic dielectric. And from this we can obtain that oh no, we don't need this. Why I have written this, I don't know. We don't need this. We can use this formula directly. We can use directly this without transformation. Epsilon 1 epsilon 0 e1 n is equal to epsilon 2 epsilon 0 epsilon 0 e to n and as a result we have got that epsilon 1 e 1n is equal to epsilon 2 e 2n. Okay, this is the second condition on the border between two dielectrics or dielectric vacuum. Okay. Do you have any questions? No questions. No questions. No questions. So what about it was normal? It was normal part of displacement vector or vector of electric field intensity. And what about tangential? What about tangent or tangential part? Tangent or tangential part. We don't have any free charges. I have said that we don't have free charges, and if we don't have any free charges, uh, it cannot make any effect on tangential part of electric field intensity. So because of this, we have that E1 tangential is equal to E2 tangential. And from this, we have that E is equal to D divided by epsilon 0, and it means that D1 tau divided by epsilon 1 epsilon 0 is equal to D2 tau divided by epsilon 2 epsilon 0 epsilon 2 epsilon 0, and from this we have that epsilon 2 multiplied by D1 tangential, and this is equal to epsilon 1 D2 tangential. Okay, do you have any questions about the conditions on the border of dielectric vacuum or two dielectrics? No questions. No questions. Okay. Okay, good. If there is no questions, I have to clean some place. I have to clean some place on the screen, and we need to write these conditions in red frame, in the same red frame. Conditions on a border between two dielectrics, or on a border between Electric and vacuum. Dielectric and vacuum. Dielectric and vacuum. According to this, we have that so that's all about electrostatic field in dielectrics. Okay, do you have any questions about this? Do you have any questions? No questions. Okay, so let's have a look at conductors. Let's learn some properties of conductors. In electrostatic field. Conductors. Conductors are a type of materials, a type of substances that may conduct electric current. Conductors may conduct electric current, and because of this property, they are called conductors, because they can conduct electric current. And this property is a result of presence of free charges, of many free charges inside conductor. Conductor has free charges. Free charges can be easily moved in conductor, and these free charges can carry electric current. And so because of free charges, conductor may conduct electric current. And let's have a look. Let's have a look at some conductor in vacuum. This is some conductor in vacuum. There is a charge Q. There is charge Q on this conductor. What can we say about electric field intensity? About electric field intensity inside this conductor. What about electric field intensity? Let's think about this. If E I'll write it here. If E is not zero, if electric field intensity is not zero, electric charge will move inside the conductor. It will move inside the conductor because there is interaction between electric field and electric charge. There is electrostatic interaction, and because of this interaction, electric charge will move. It means that here will be electric current. But electric current electric current needs some energy, needs some energy support to continue, because during electric current we always have energy loss, and it is necessary to compensate this energy loss, and energy cannot be obtained from electrostatic field only, because as you can remember from our previous lessons, that work of electrostatic field can be calculated by phi1 minus phi1 minus phi2. Phi1 minus phi2. Difference between electric potentials. And but the conductor is in limited part of space. So the trajectory of charge, if charge moves, the trajectory will be a closed line. Trajectory of Q will be closed line. And if we have closed line, the beginning of this line is in the end of this line, if the line is closed. And it means that electric potential in the beginning and in the end of trajectory is the same, and it means that it is equal to 0. It is equal to 0 for closed trajectory. And it means that electrostatic field cannot support constant electric current. Electric current is impossible in electrostatic field only. It is necessary something else to support electric current. So if there is electric field inside the conductor, there will be electric current, but electric current is impossible in electrostatic field. And this contradiction means that there is no any electrostatic field. Inside the conductor. There is no any electrostatic field inside the conductor. And because of this, what can we say about charge, electric charge inside the conductor in its volume? As we can remember, Gauss law for electric field intensity. According to this, electric charge density is equal to divergence of electric field intensity. And because of this, if E is equal to 0, Q inside of conductor is equal to 0. So there is no electric charge. There is no electric charge inside the conductor. And we can always remember that electric field intensity is equal to minus gradient of electrostatic potential. But gradient is what is this? It is sum of derivatives, partial derivatives, d phi by dx I plus d phi by dz j and plus d phi. Sorry, I have made a mistake. Here is it y dz k vector. This is sum of derivatives. But electric field intensity is equal to 0. And if derivative is equal to 0, the function is constant. Function is constant. So phi inside the conductor, phi is equal to constant. Phi is always equal to electric potential is equal to constant inside the conductor. So it means that all charge of conductor will be on its surface. All charge will be on the surface of conductor. On the surface of conductor, and there is no charge inside the conductor. And what about electrostatic field? What about electrostatic field? And electrostatic field can be shown like this. For example, can be shown like this. Can be shown like this. And electric field intensity vector is always perpendicular to the surface of conductor. Why? Because in the other case, electric field intensity will lead to electric current on this surface. But as we have said before, that electrostatic field cannot support stable electric current. And because of this, electric field intensity vector is always perpendicular to the surface of conductor. Okay, do you have any questions about this? Do you have any questions about this? No questions. No questions. Okay, if there is no questions, let's have a look. Let's have a look on the surface of conductor. Surface of conductor. Yes, surface of conductor. And I will draw some infinitely small cylinder. Infinitely small cylinder. Infinitely small cylinder. Its axis is perpendicular to the surface of conductor. Axis of cylinder is perpendicular to the surface of conductor. This is cylinder. This cylinder is infinitely small. The area of its base is equal to ds. This area is equal to ds. It is infinitely small. It is infinitely small. And as we have said before, electric field intensity vector is also perpendicular to the surface of electric conductor. And here it is perpendicular to the conductor. It means that according to Gauss law, we will have that d multiplied by ds without integral, because ds is infinitely small. And here we can see that E has the same direction as ds. This double arrow means that E has the same direction as ds. And this means that d also has the same direction as ds, because this is because we are learning only isotropic substances. In such substances, the directions of electric displacement vector and electric field intensity vector directions are the same. So ds is equal to ds cosine cosine 0, and this is equal to ds. So it is equal to ds. So this scalar product or dot product can be easily calculated. In this case, can be easily calculated. So it may be simply rewritten without vectors. Without vectors, and this is equal to Q free charge inside the cylinder, and this free charge inside the cylinder is equal to surface charge density sigma, charge density sigma multiplied by ds. So near the surface of conductor, electric displacement vector is equal to electric charge density, surface charge density. Okay, do you have any questions? Do you have any questions about this? No questions. No.
Teacher, what this is what?
Sigma.
Sigma, okay.
Greek letter sigma. This is
okay. Thank you, teacher.
okay. So I'll clean some place. Some place. So near surface of conductor. Near surface of conductor. We always have that modulus of electric displacement vector is equal to surface charge density. And always. This is always. And what about electric field intensity? Electric field intensity, we have learned that in vacuum or in isotropic dielectrics, it can be written without vectors, because electric permittivity of isotropic dielectric or in vacuum is a simple number. And because of this, we have that E is equal to D divided by epsilon 0. Epsilon 0. So we have E is equal to sigma divided by epsilon 0. And this is for dielectrics. For conductor in dielectric or vacuum. Isotropic dielectric or vacuum. On this. Okay, yes. And it is necessary to draw red frame for this. Okay, do you have any questions about this? And do you have any questions about this? No questions. Okay. We have just learned some properties of conductor in vacuum. For conductor in vacuum or for conductor in dielectric, in case when there is no any charges, near this conductor. So we have charges on the conductor, but we don't have charges near this. If there are some charges near conductor, situation will be similar. This is conductor. Inside the conductor, there is no electrostatic field inside the conductor, and potential is constant. Potential is constant inside the conductor. And what about external electrostatic field? What about external electrostatic field? It will look in some way like this. It will look in some way like this. The electric field will look in some way like this. Here will be it will be normal to the surface of conductor. It will be normal to the surface of conductor near it. And there in external electric field, charge on the surface of conductor will be redistributed, and this redistribution of surface charge, is known as electric induction. Because of electric induction, here we will have negative charges, and here we will have positive charges. Here we will have positive charges. But there is no field, and there is no charge inside the conductor. Inside the conductor. There is no charge and there is no field inside the conductor. Okay, is it clear or not? And these properties, the absence of electric field inside the conductor, can be used in practice in industry. Maybe you have heard about secured coaxial cable or coaxial wire. What is this? This is wire. I'll draw a cross section of this. This is a wire. This is wire inside cylindrical conductor. Wire inside cylindrical conductor. And here we have, in the middle, here we have signal, signal transmission, and nothing can prevent this signal transmission because a wire is inside conductor. So conductor is a shield. Conductor provides so-called shielding or shield effect. It is known as shielding. So there is no electric field. There is no electric field inside conductor, so we can transmit our signal without any interruptions. Even if there is some field outside. This is the use in industry. Shielding effect. Okay, and as we can see, if there is conductor without any charges near this, the electric field displacement will be proportional to sigma, and it will be proportional to electric charge. So I mean that it is equal to sigma, and sigma is proportional to electric charge on the surface of conductor. And it means that electric field intensity is proportional to charge on surface, and we know that electric potential is equal to minus integral from R0 to R E dl plus phi 0 plus phi 0. We can choose any phi 0. Let's choose it. Let's choose it equal to 0. And because of this, we have that Q electric charge is proportional to electric potential, and it can be written like this: Q is equal to C multiplied by phi. Q is equal to C multiplied by phi. C is a coefficient, and it is known as capacitance. C is 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 capacitance. Units of capacitance is farads. Farad unit of capacitance. Farad is a unit for capacitance, and in short form, it can be written as F. Farad is unit of capacitance, and as I have said, charges near the surface of conductor will lead to a redistribution to electric induction, and so a redistribution of electric charges on its surface. And it means that presence of electric charges near the surface of conductor will change its capacitance. So presence of charges near the surface of conductor will change its capacitance. And it also, this property, dependence of capacitance on presence of electric charges, can be used in industry. For example, in some sensors, and for example, in your mobile phones, in your gadgets, the sensor touch screen, capacitive touch screen. When you put your finger on the screen, or when you move your finger near the screen, the capacitance near your finger changes, and it can be detected by the systems, and in such way your phone feels touching of this. So it was an example of use of dependence of capacitance of electric charges near the surface of conductor. Okay, do you have any questions? Do you have any questions about this? No questions. Okay, so thank you for your attention.